One more curve sketching example, and this one has a radical in it. Yay! Okay, so first we look at the domain. What numbers cannot go into this function? Well, I can't divide by 0, so x cannot be 0, and I can't take the square root of a negative number, so I have to figure out what would make this negative. Oh, nothing, because it's squared, right? Okay, so the only domain restriction I have is that x cannot equal 0, because I can't put it at 0 in the denominator. Do I have any holes? No, because nothing cancels out top and bottom, so I have none. Now, if you remember, this kind of behaves like x plus 1 over the absolute value of x, because if I take some number and I square it, and then I take the square root of it, I basically undo the squaring, right? I just kind of like get back what I put in, except I always get a positive number back. Because if I take some number, say 2, and I square it, 4, take the square root, 2, I come right back to 2. But if I take negative 2 and I square it, 4, take the square root, 2, I come back to the positive version of that number. So anytime you see something like this, the square root of x squared, it basically behaves like absolute value of x. So what about my y-intercepts? Well, we have an asymptote at x equals 0, don't we? Because that's what we have our domain restriction, and it's not a hole, so it has to be an asymptote. So I have an asymptote there at x equals 0, therefore there is definitely not a y-intercept. So none. What about an x-intercept? Well, when y equals 0, what would make this whole thing equal to 0? Well, x plus 1 would have to equal 0. Therefore, when x equals negative 1, I have an intercept. So, negative 1, 0 is my x-intercept, so I can go ahead and graph that. Sometimes I graph right along as I'm doing it, sometimes I wait till the end. Just depends on your choice. All right. Now we look at end behavior. Now because this has a radical in it, we have to look from the left and we have to look from the right because this behaves differently. Remember, they can have two horizontal asymptotes. So we're looking for horizontal asymptotes here, and what's going on? All right, the limit as x approaches infinity the limit as x approaches infinity of this function. Well, let's see. I have a huge number over itself, basically, right? I have like 1,000,001 over 1,000,000. Well, nobody cares about that 1. So basically, I have a huge positive number over a huge positive number. Therefore, I'm going to positive, not positive infinity, positive 1, because it's a number over itself. What about the limit as x approaches negative infinity? Well, I'd have a huge negative number over a huge positive number because I'm going to take the absolute value, so that equals negative 1. So I have an asymptote on the left. As I get to negative infinity, I have an asymptote of negative 1, and as I get to the right, I have an asymptote of positive 1. Okay. Last but not least, I forgot to talk about whether that vertical asymptote is even or odd. Well, let's look at the function that created it, or the factor that created it. It's this x squared right here, right? Since it's squared, this would be an even asymptote. So we know it's either going to go this way, down like this, or it's going to go up. Well, it has to be going through this point, which means it has to be going up. From this point, it can't go down, because it would cross over its horizontal asymptote, so it has to go up. The other way we can find this is we can look at the limit. We can look at the limit as x approaches 0 from the left, and that would be numbers just smaller than 0. So we would have positive over a positive, so that would be positive infinity. And then the limit as x approaches 0 from the right would still be a positive over a positive, so they're both going to positive infinity, so I know that that one's got to go to positive infinity and that one's got to go to positive infinity. Then it's going to come down, it's going to approach its horizontal asymptote on this side and its horizontal asymptote on this side. And there you go, you're done.